Welcome to the video lecture on comparison tests. Let's do a quick summary so far of all of the tests that we know to prove whether or not a series converges or diverges. Let's start with convergence tests. If we know that we have a geometric series of the form a r to the n, it will converge if this r is in absolute value between 0 and 1. If you have a p series, which is of the form 1 over n to the p, then that will converge if p is greater than 1. The integral test tells us that the infinite series a sub n converges if the integral from 1 to infinity of f of x dx converges, where this f of x function is the same as this a sub n. You need your function f to be positive, continuous, and decreasing in order to apply the integral test. And then we also have partial sums. If we have a formula for our partial sum, our s sub n, and the limit of that goes to some value s and converges, then that means the infinite series converges to that s as well. Now for our divergence tests. If you have a geometric series, that will diverge if the common ratio r in absolute value is greater than or equal to 1. If you have a p series of the form 1 over n to the p, that's going to diverge if your p is between 0 and 1 or equal to 1. In the integral test, your infinite series a sub n will diverge if the integral from 1 to infinity diverges. Again, you need to show that f is positive, continuous, and decreasing first. Partial sums, if you have a formula for your nth partial sum s sub n and the limit of that as n goes to infinity diverges, then the infinite series has to diverge as well. And then we also have one additional test for divergence called the nth term test, and it says that if the limit of the a sub n as n goes to infinity does not equal to 0, then the infinite series of a sub n diverges. And it's important to note that if that limit does equal to 0, you can't tell convergence or divergence. You would have to try one of your other tests to see whether or not it converges or diverges. So what we're going to talk about today is a couple of new tests that we're going to add to our toolbox of tests to determine convergence and divergence. And the first test we're going to discuss is the direct comparison test. What this says is that if you have two series, a sub n and b sub n, where they're both positive, greater than 0, and a sub n is smaller, less than or equal to b sub n for every n. And note that this implies that all the terms are positive. However, if the terms are all positive after a particular term, then you can still apply this direct comparison test. Now there's two possible conclusions using this comparison test. If your bigger series, the b sub n, converges, then your smaller series, a sub n, will converge. Okay, so if the larger series converges, then the smaller series must converge as well. The other possible conclusion is that if your smaller series, a sub n, diverges, then the bigger series, b sub n, must diverge as well. So if the smaller series diverges, then the larger series must diverge. Okay, so we're going to prove these two statements here. So first let's assume that the sum of b sub n does converge, and let's let L represent its actual sum. And we're going to let s sub n be the nth partial sum of all these a terms, so a sub 1 plus a sub 2 all the way up to a sub n. So we have two conclusions that we can make based on the fact that we know that a sub n is greater than 0 and a sub n is less than or equal to b sub n. Since our a sub n's are all positive, then these nth partial sums must either stay the same size or continue to get bigger. In other words, this sequence of partial sums is increasing because you're just adding on the next term each time, and each term is positive. So we would say that this sequence s sub 1, s sub 2, s sub 3 is non-decreasing. That's just a fancy way of saying that it increases or stays the same. And that's because all of our a sub n's are positive. We also know that all of our a sub n's are less than or equal to b sub n. And b sub n is converging. So that means that b sub n, which has a sum of L, its partial sums approaching L as well. And if each of the nth partial sums of A sub n is smaller than the nth partial sum of B sub n, then the nth partial sum of the A sub n's must be bounded from above by L as well. So we also know that since A sub n is less than or equal to B sub n, then this sequence S sub 1, S sub 2, S sub 3, and so forth is bounded from above by L, the sum of the B sub n terms. Since these are all smaller, their sum has to be less than or equal to the sum of the B sub n's, which was L. So we had a theorem a couple of video lectures back that said if you have a sequence which is non-decreasing and bounded, then it must converge, because we're bounded from above by L, but we're continuing to increase, so we must converge. So there's a theorem that says that this sequence of partial sums must converge. So the limit as n goes to infinity of S sub n must converge, which implies that this sum, which is what our limit of our nth partial sums is equal to, must converge as well. Since these partial sums, S1, S2, S3, and so forth, is non-decreasing and bounded from above. Okay? So that proves that if your bigger series converges, then your smaller series must converge as well. It has nowhere else to go. All right? If we take a look at the other conclusion that we can make, let's look at the smaller series A sub n, and let's assume that it diverges. So let's let S sub n be the nth partial sum of these A terms. So A1 plus A2 plus A sub n, or all the way up to A sub n. Let's let S sub n bar be the nth partial sum of our B terms. So B sub 1 plus B sub 2 all the way up to B sub n. So since we know that, again, A sub n is in between 0 and B sub n, then since all of these A terms are less than or equal to all of these B terms, then we know that the nth partial sum of A must be less than or equal to the nth partial sum of the B terms. And that has to be true for all n. So what that tells us is that the limit then, as we go to infinity, of our nth partial sum of the A terms must be less than or equal to the limit of the nth partial sum of the B terms. So this inequality is still maintained in the limit. But if A sub n diverges, then that means its limit of its nth partial sum goes to infinity, which forces the limit of our nth partial sum of the B terms, which is the same thing as the sum of the B terms, as I go to infinity, that must be greater than or equal to infinity. And that can only happen if this limit and this sum diverges. So therefore, this summation must diverge, because it's supposed to be greater than or equal to infinity. Okay? So conclusive comparisons can be made between fractions with either like numerators or like denominators. When we're doing our comparison tests, we're usually going to look at those numerators or denominators and try to make them be the same or similar to each other so that we can make a comparison. And what we're trying to compare it to is a known series. So something like a geometric series that you already know converges or diverges, or a p-series that you already know converges or diverges. So for example, if I want to show that the sum from 1 to infinity of 1 over n cubed plus 1 either converges or diverges, what I want to compare it to is something that I know converges or diverges. So what could we compare this to? Well, it looks pretty similar to just the sum from 1 to infinity of 1 over n cubed. And that we know converges because it is a p-series with p equal to 3, which is greater than 1. And we know that if your p is greater than 1, then you're going to converge. So in order to make our comparison, we need to show this term by term relationship that our a sub n's are either less than or equal to or greater than or equal to our b sub n's. So we need to see how these two terms, a sub n and b sub n, compare. So what you can notice is obviously n cubed equals to n cubed. So how does n cubed plus 1 compare to n cubed? Well, we're adding 1 to it, so it's got to be greater than or equal to n cubed. Now if you take 1 over n cubed plus 1 and compare it to 1 over n cubed, how would those compare? Well, here the denominator is bigger, so the fraction must be smaller. So this inequality flips to a less than or equal to sign. And obviously both of these are going to be greater than 0 because we're using only positive n's. So this relationship is true for every n. And now we've just shown, this is all we need to show for the comparison test, that the 1 over n cubed is now the bigger series because it's greater than the other one, and it converges because it was a p-series. So if your bigger series converges, then that forces the smaller series to converge as well. So the comparison test tells us then that the sum of 1 over n cubed plus 1 must converge as well. So really all you're showing for this comparison test is this inequality, that you either have the smaller or the larger series, and that series that you're comparing it to either converges or diverges. Let's try another example. Here we want to look at the convergence or divergence of 1 over the square root of n minus 1. So what could we compare this to? What does it look almost like? Well, if you ignore that minus 1 in there, it's almost like 1 over square root of n. Now, does that series right there converge or diverge? Well, that is like a 1 over n to the 1/2. So it's a p-series, and it's a p-series with a p equal to 1/2, which is less than 1, which means this is a divergent series. Okay, so the series that we're comparing it to diverges. So now let's compare this series, the known one, to the unknown one, and we want to establish an inequality relationship between the two. So if we look at our denominators, we're trying to compare the square root of n minus 1 to the square root of n. So the square root of n, if you subtract 1 from that, that's going to make it get smaller. So the square root of n minus 1 must be smaller than the square root of n. So then if we take the reciprocal of this and compare these two fractions, if this denominator is smaller, that's going to make this fraction get bigger. So this inequality would be a greater than symbol. And obviously these are, again, both going to be positive because we're assuming that n is starting at 2 and going to infinity. So this is definitely going to be greater than 0 for all n. So we've established that relationship that we need, and this one is the biggest series, the bigger one. And the known one that we already know diverges is the smaller one. And the smaller one, the smaller series here, diverges. That means that the bigger series, which has to be larger than this, must diverge as well. So the comparison test tells us that the sum of 1 over square root of n minus 1 from n equals 2 to infinity must diverge, because the smaller series that we were comparing it to, we know diverges as well. Okay, let's take a look at the sum from 1 to infinity of 2 to the n over 3 to the n plus 5. So using our comparison test again, what does this look like we could compare it to? Again, ignoring that plus 5 in the denominator, this looks pretty similar to a 2 to the n over 3 to the n. And if you factor out that power, you could rewrite this as 2/3 to the n. Is that a series that converges or diverges? Well, it's geometric because it's a constant being raised to a power. So this is a geometric series. Your r here is that 2/3, and since that's a fraction less than 1, then that means that this known series here must converge. So what we want to show is that this known series is bigger than this series here, so that if the bigger series converges, that forces the smaller one to converge as well. So how can we compare these two? Well, think about 2 to the n over 3 to the n plus 5 and how that relates to 2/3 raised to the n, which remember is the same as 2 to the n over 3 to the n. If you look at these two denominators, the numerators are already the same. So if you look just at the bottom, we're adding to make this denominator bigger, which means the fraction as a whole is smaller. So this has to be less than or equal to right here. And then these are obviously going to be positive because we're using all positive terms here and positive exponents. So this is true for all n. So as we have shown here, we have a bigger series which we know converges. So that forces the smaller series to have to converge as well by the comparison test. Okay. Next example, 1 over the square root of n cubed plus 1. So what could we compare this to? Look at what dominates. 1 over square root of n cubed. So if we look at that as 1 over the square root of n cubed, think of rewriting that as an exponent. Square root of n cubed is the same as the power 3/2 because a square root has a fractional power. The 2 goes in the bottom, the 3 goes in the top. So does this series here converge or diverge? Well, it's a piece series with a p equal to 3/2, which is greater than 1, so that means it converges. So what we want to show is that if this converges, it needs to be the bigger series to force the smaller series to converge. So let's look at our fractions here again. If we have 1 over the square root of n cubed plus 1, and we compare that to 1 over the square root of n cubed, which we know is the same as n to the 3/2, this is adding 1 to your denominator, which is making the denominator get bigger, which makes the whole fraction get smaller. So this is going to have to be less than or equal to 0, and both of these are obviously positive for positive n's. So this is true for all n. So again, what we have here is that our known series is the bigger one, and it converges because it's a piece series. Therefore, by the comparison test, the sum of 1 over the square root of n cubed plus 1 must converge as well. On the next example here, we have a trig function. So let me show you how to handle these. We want to look at the sum from 1 to infinity of the absolute value of secant of n over n. So what could we possibly compare this to? Well, what you want to keep in mind is that with trig functions, you know that cosine and sine are bounded between -1 and 1. They oscillate between -1 and 1. What you would want to know about the reciprocal, so for example secant, which is the reciprocal of cosine, is that it's actually greater than or equal to 1 in absolute value. So what we can look at is the fact that the secant of n we know is going to be larger than 1 or equal to 1 in absolute value. And you can look at the graph of your secant function to recall that. It looks like these U shapes like this. And they all start at 1 or -1 and go down or go up. So they're either always above 1 or below -1. So in absolute value, we know that secant is always greater than or equal to 1. So what we could do then to get this particular series is we could divide both sides by n. And since n is positive, that's not going to flip around our inequality symbol. So this inequality is still maintained. So the absolute value of secant of n over n is greater than or equal to 1 over n, and both of these are obviously going to be positive for all n. So the one that we're comparing this guy to is 1 over n. And this is actually the smaller series this time because it's smaller than our secant of n over n. Does it converge or diverge? Well, it's the harmonic series. It's a p series with your p being equal to 1. So it diverges because it's the harmonic series. And if the smaller series diverges, then that forces the bigger series to have to diverge as well. So by the comparison test, the absolute value of secant of n over n must diverge as well. So when you're dealing with these trig functions and you're trying to do a comparison test, usually you can compare it to 1. And either, depending on the trig function, it'll be less than or greater than 1. So let's take a look at this next example, 1 over 2 plus square root of n. So instinct would say to compare this to 1 over square root of n, because we can kind of ignore that 2 as n gets really, really large and just look at the dominant terms. So we would probably think to compare this to 1 over square root of n, which is like a 1 over n to the 1/2. And that's a p series with p equaling a half, which is less than 1, so it will diverge. So in order for the comparison test to work here, this one needs to be the smaller series so that the bigger series is forced to go to infinity as well, or forced to diverge as well. So we need to establish the relationship that this one is smaller than this one. So if we look at our two denominators, our two fractions actually, 1 over square root of n and 1 over 2 plus square root of n, which we know is the same as that 1 over n to the 1/2. This is adding to our denominator, which is actually going to make the fraction get smaller. So the inequality that's actually true here is a less than or equal to sign, and that's not what we want. In order for the comparison test to work, we need our known series here, the divergent one, to be the smaller one so that the bigger one is forced to diverge also. So because this inequality relationship isn't the way we want it to be, then we can't use the comparison test. At least we can't use the comparison test with this known series. So what we're going to have to try to do is try comparing it to something else. So let's try comparing it to a different series, potentially something that diverges. We have a good suspicion here that this probably does diverge. We just can't get that term by term comparison to be the right way. So let's pick another divergent series, and I'm going to pick one like 1 over n, that harmonic series. So we know that this diverges because it's harmonic. Now unfortunately, 1 over n doesn't compare nicely to 1 over 2 plus square root of n, at least visually. We can't just look at denominators and see the relationship. What we're hoping is that 1 over n is less than or equal to 1 over 2 plus square root of n, so that it will be the smaller series. And we know that it diverges, so that would force the bigger series to diverge as well. So in order to show this, since we can't really just look at the denominators and sort of talk it through about whether one's bigger or not, what we are going to have to look at in this kind of an example is our calculator. What I recommend is just pulling up your calculator and typing into y equals the function over here 1 over n, and in y2 your function 1 over 2 plus square root of n. So let's pull up the calculator. In y1 I have that divergence series 1 over x, and in y2 I have 1 over 2 plus square root of x. What we're hoping again is that the 1 over x, the function in y1, is smaller than the function in y2. So let's look at our table and see if that's true. Now initially 1 is bigger than 0.3, 0.5 is bigger than 0.29, 0.3 is bigger than 0.26, And then at 4, 0.25 equals to 0.25, so now they're actually equal. And then from 5 on, we get 0.2 is smaller than 0.23, 0.16 is smaller than 0.22, 0.14 is smaller than 0.21, and you could continue down to verify that from this point on, all of these in the first column here in y1 are smaller than all the values in y2. That change happened at 4. So less than 4, so for terms 1, 2, and 3, the y1s were bigger. But when we got to 4, they were equal, and then they got less. So remember that if you can show this term-by-term relationship for a, maybe the first few terms may not satisfy it, but as long as you can eventually find some value for n where it does satisfy that relationship for the rest of the terms on up to infinity, then you'll still have that convergence or divergence that you suspect. So what we can say here is that this is true for all n greater than or equal to 4. And as long as that's just a finite number of terms where this may not be satisfied, that's okay. You can disregard those first 3 or 4 terms. As long as it's maintained from 4 on to infinity, you're okay. So this relationship is satisfied, which means that we can use our comparison test. We just had to use a different series. And since the smaller series diverged, that means the larger series, which is our 1 over 2 plus square root of n, must diverge as well. So oftentimes a given series closely resembles a geometric series or a p-series, but you can't establish the term-by-term comparison necessary to apply the direct comparison test, like this last example, unless you get creative and can find some function that actually works. So an alternative is a new test that we're going to learn called the limit comparison test, and this is useful in these situations or circumstances where it's hard to show that term-by-term comparison, that inequality relationship that you need to have true to use the direct comparison test. So this test that we're going to learn now, very similar, but it's going to be a different kind of application. We're going to use it in a different way. It's called the limit comparison test. You want to assume or suppose that your a sub n and your b sub n are both greater than 0 so that you have positive terms. And all we're going to do is take the limit as n goes to infinity of our a sub n over our b sub n. And if that limit exists and equals to some number L that's greater than 0, then either both of these sums converge or both of them diverge. So note that when we're using this limit comparison test, usually we let the a sub n series be the one that we're trying to figure out, and we let the b sub n series be the known series that you already know is convergent or divergent. So you do the unknown series on top divided by the known series on the bottom. Now a couple of addendums to this. If you don't get a limit that's positive, greater than 0, and finite, then you potentially could be stuck and you can't use the limit comparison test except in these two cases. If this limit turns out to be 0, then if you know that your known series in the bottom converges, then that means the unknown series in the top must also converge. If your limit goes to infinity and your bottom known series diverges, then that means your top unknown series must be divergent as well. And the reasoning behind that is kind of the following. Suppose that if you know that this limit equals to 0, then that means your b sub n on the bottom must be overpowering the a sub n. It means that the b sub n in the bottom is going to infinity faster, making the fraction go to 0. So you can kind of think of this b sub n as being the bigger, more powerful series. So in the idea of the comparison test, if the bigger series converges, then so does the smaller series. And then in the second case, if your limit is going to infinity, then that means the top function, a sub n, is actually more powerful. It's going to infinity faster than the bottom is. So if you think in terms of this comparison test, your a sub n is like the bigger series. So if b sub n diverges, then so does the bigger series a sub n. So an example here would be the sum from 1 to infinity of 1 over an plus b, which is called the general harmonic series. It's just the harmonic series with some coefficient possibly in front of n plus a constant on the side. And we're assuming here that the a and the b are both positive numbers. So we could try to do a comparison test here and compare this to the series 1 over n, which we know diverges because it's the harmonic series, p series equal to 1. But it would be hard to establish that term-by-term relationship, because if you have an plus b, with your a and your b being positive, then that means this denominator is bigger than this one, so the fraction is smaller than this. And that means the known series we have here is actually bigger than this one, and we want the reverse relationship if we want to show that our general harmonic series diverges. So instead, what we're going to do, since we can't establish that term-by-term comparison using those inequalities, we're going to use the limit comparison test. So what the limit comparison test tells us to do is to take the limit, as n goes to infinity, of your unknown series. So that's this one right here. That's the one that goes on top, over your known series on the bottom. Now you're going to have to do a little bit of algebra here. I'm just going to multiply by the reciprocal. So this becomes the limit, as n goes to infinity, of n over an plus b. And now at this point, if you plug in infinity, this is just going to be infinity over infinity. So you could use L'Hopital's rule, and the derivative on top goes to 1. The derivative on the bottom just goes to this a. You could also have just looked here and said, well, since these powers match in the long run as n goes to infinity, this is going to be dominated by n over an, which is just going to reduce to 1 over a. Now, since 1 over a is a constant, then that's what this limit is going to be. And remember, we know that a is positive, so 1 over a is positive. And that's what we're trying to show. We're trying to get an actual finite limit and some L right here that's greater than 0. And we did. So what that means is that if your known series diverges, then your unknown series must diverge as well. They have to do the same thing. So the limit comparison test tells us that this general harmonic series must diverge as well. So if we try 1 over 2 to the n minus 5, what could we compare this to? Again, we're going to do the same idea that we did with our direct comparison test. Look at kind of what dominates here. This minus 5 on the side is really going to become insignificant as n gets really, really large. So your instinct should be to compare this to just 1 over 2 to the n. And that, if you want to rewrite it, is the same as 1/2 to the n, which is geometric. So this is a geometric series because it's a constant raised to a power, and the r is that 1/2, which is a fraction less than 1. So this converges. So our known series converges. So if we do our limit comparison test and we get an actual limit, then that means since this converges, so must this one as well. So let's see what happens with our limit comparison test. We need the limit as n goes to infinity of your unknown function on the top over your known function on the bottom, and I'm just going to use 1 over 2 to the n. Multiplying by the reciprocal, this becomes the limit as n goes to infinity of 2 to the n over 2 to the n minus 5. Right now, initially, when I plug in infinity, this is going to be infinity on the top and infinity on the bottom. So if I use L'Hopital's rule, The derivative of 2 to the n is 2 to the n back again times the ln of 2, since your base is not an e. The derivative on the bottom is also 2 to the n ln of 2, and the minus 5 goes to 0. So these all cancel, which means this limit is 1, which is definitely something greater than 0, and that's what we want. So the limit comparison test tells us then that this series here does and acts the same way as our known series. And since this known series converged, then so does our unknown series. How about the sum from n equals 1 to infinity of 5n minus 3 over n squared minus 2n plus 5? So we want to compare this to something, and the idea is to try and look to see what would dominate here. On top, we have that 5n. On the bottom, we have an n squared. So this is acting kind of like a 5 over n. You can disregard the constant on the top. We're going to just compare this to that power of n. So we have a 1 over n basically is what this is acting like, disregarding all the constants and smaller ordered terms. So what do we know about the sum from 1 to infinity of 1 over n? We know that it diverges because it's the harmonic series. P series equal to 1. So it would be very difficult to establish that term by term comparison for these because you have such a mess with this unknown function. So this is ideal for that limit comparison test, looking at the limit as n goes to infinity of your unknown series on top and your known series on the bottom. And I'm going to multiply by the reciprocal. So this becomes the limit as n goes to infinity of, when I distribute this n across, we get 5n squared minus 3n over n squared minus 2n plus 5. Now you can do L'Hopital's rule here if you like. Initially this is infinity over infinity, or you can just look at the dominant terms. These are your dominant terms because they have the highest power, and that is going to reduce to just a 5. So this limit will go to 5, which is greater than 0. So that means by the limit comparison test, this series that we were given must act the same way as our known series, which was that harmonic, which we knew diverged. So this series must diverge as well. Alright, the next example, the sum from 1 to infinity of n over n plus 1 times 2 to the n minus 1. So when you're thinking about what to compare this to, look at what dominates. On top, we obviously have that n dominating. On the bottom, the n plus 1, the dominant term there is the n. And then we have this 2 to the n minus 1 as well. The n's are going to cancel each other out in the long run. So this is acting like that 2 to the n. And this minus 1 is just, again, an insignificant term as n gets really, really big. So in the long run, what's going to dominate here is 1 over 2 to the n. So that's what you want to compare this to. You want to find a very simple function that you can compare it to, and it has to be something that you know what it does, whether it converges or diverges. And recall that this 1 over 2 to the n, if you need to think of it as 1/2 to the n, recognize that it's geometric. Okay, so this is geometric with your common ratio r equaling 1/2, which is a fraction less than 1, so it converges. So if we do our limit comparison test, we're going to look at the limit as n goes to infinity of the unknown function on top over the known function. And I'm going to multiply by the reciprocal. So this becomes the limit as n goes to infinity of n times 2 to the n over n plus 1 times 2 to the n minus 1. So to take the limit of this, obviously n's going really, really large, so this is going to be infinity over infinity. So we can do a little bit of L'Hopital's rule here if you like, or you can just do some simplifying. 2 to the n minus 1 is really the same as 2 to the n times 2 to the negative 1, breaking up that power. If you have the same base, you're adding the powers, so these two expressions are the same. And 1 over 2 to the negative 1 is the same as 2 on top, flipping this up, times that n, 2 to the n, n plus 1, and 2 to the n. So by breaking up this power here, we can cancel these guys out, which leaves me with a much simpler looking function, and it'll be much simpler to deal with. You won't have to use L'Hopital's rule at all, because now those 2 to the n's are gone, and what's going to dominate this is that 2 to the n over n, which is just going to go to 2, and that's obviously greater than 0. So break up that power to move that 2 up to the top, and that makes it easier for you to just go ahead and cancel that exponential part right away. So by the limit comparison test, this series that we were looking at, n over n plus 1 times 2 to the n minus 1, is going to act the same way that our 1 over 2 to the n acted, and that was geometric, which converged. So that means this series converges as well. Okay, our last example here, we've got the sum from 1 to infinity of 1 over n plus square root of n squared plus 1. Again, looking at what dominates, we have a 1 on top, and then we have an n here, and the square root of n squared in the long run is going to reduce to just square root of n, and that 1 becomes insignificant on the side. So this is acting like a 1 over 2n. If I ignore the constants, this is really like a 1 over n, which is the harmonic series, which we know diverges. So we're going to compare this to the harmonic. So we know that this known series diverges because it's harmonic. So let's see what happens in our limit. So we're going to take the limit as n goes to infinity of our unknown function over our known function. And I'm going to multiply by the reciprocal. So we get an n over n plus square root of n squared plus 1. Now you can be fancy here if you want. I'll show you the formal way to do this, or you can just look at those dominant terms. In the dominant term, on top would be the n, and on the bottom we have that n, and the square root of n squared again is going to go to n as well. So this is really acting like n over 2n, which is going to go to a half. So that's what the limit actually is. If you wanted to be formal about this, you could use L'Hopital's rule. Since initially this is infinity over infinity, the derivative on the top goes to 1, the derivative of n goes to 1, and the derivative of square root of n squared plus 1 would become 1/2 n squared plus 1 to the negative 1/2 times 2n. The 1/2 and the 2 cancel, and this is going to be 1 over 1 plus n over the square root of n squared plus 1. In the long run, this part right here is acting like n over n, which is going to go to 1. So you've got 1 over 1 plus 1, which is that 1/2, which is positive, greater than 0. So by our limit comparison test, the known series that we had was that harmonic, which we knew diverged. So the unknown series must diverge as well. So just a note here, when you're using either the comparison test or the limit comparison test, we are able to determine whether the series converges or diverges. But if it converges, we don't know what it converges to, nor do we have a way to approximate the sum of the series. So these are powerful tests, but they don't tell us everything. They just tell us whether they converge or diverge, but they don't actually tell us what it converges to, what that sum actually is. And you want to keep in mind that this comparison test, the direct comparison test, is most useful when your function looks almost identical or very, very similar to a known series, and you can establish that term by term comparison. If that's too difficult to do, or your function is too messy, then I would encourage you to use that limit comparison test instead and compare it to whatever the function is being dominated by. Alright, that concludes our video lecture on comparison tests. Good luck!